Have you ever wondered how a computer can possibly outthink a chess grandmaster? Well, it's not just about raw computing power, it's about thinking smart. Today, we're going to dive deep into alpha-beta pruning. It's this brilliant little trick that lets game-playing AIs see the future without getting totally lost in an infinite sea of possibilities.
So here's the game plan. First, we'll try to get our heads around the massive scale of the challenge that AI is facing. Then we'll introduce the smarter way to search that really changed the game. After that, we'll get into the nuts and bolts of how it all works, see its incredible real-world impact, and finally, we'll ask the big question: is this still the ultimate strategy?
All right, so before we can really appreciate the solution, we have to understand the problem. And trust me, it's an absolute computational nightmare.
Let's start with the big fundamental question, right? A game like chess isn't just about knowing how the pieces move. It's about looking ahead, anticipating what your opponent's going to do, and planning your own moves pages in advance. So how does a machine even start to do that?
Well, the basic approach is to build something called a game tree. You can just think of it like a giant flowchart of every possible future. The board right now, that's the root of the tree. Every single move you could make creates a new branch. And then, for each of those branches, you map out every possible response from your opponent, and so on and so on. So the first logical attempt to solve this is an algorithm called minimax. It's a brute force method, really. It goes down every single branch to the very end of the game, gives each outcome a score, and then works its way back up. It assumes you, the maximizer, will always pick the move with the highest score, and your opponent, the minimizer, will always pick the one with the lowest.
But here is the fatal flaw. The number of possibilities, the number of nodes you have to check, it just grows exponentially. Looking just a couple of moves ahead can mean evaluating billions or even trillions of different board positions. For a game like chess, or especially Go, trying to explore that entire tree it's just computationally impossible. You can't do it.
And this is where our hero enters the story. Because if you can't search harder, well, you've got to search smarter. You know, the name itself is the perfect metaphor, right? Just like a gardener prunes away dead or useless branches to help a tree grow stronger, this algorithm intelligently snips away useless branches from that giant game tree, which saves a massive, massive amount of work. Now, this is the most important thing to get. Alpha-beta pruning is not a guess, it's not an approximation. It finds the exact same perfect move that Minimax would have found. It just gets there so much faster because it's clever enough to realize, hey, this whole section of the future, it's a dead end. There's no point even looking. Okay, so let's get into the mechanics. How in the world does the algorithm know which branches are useless without even looking at them? Well, this is the magic part, and it all comes down to two simple values. First up, we have alpha. You can think of this as the best score, the highest value that our player, the maximizer, can guarantee for itself so far. It actually starts at negative infinity, which basically means at the beginning, our player has zero standards. It's desperate and will consider any outcome. But as it finds better moves, that alpha value goes up. And on the other side of the coin, you've got beta. This is the best score, meaning the lowest value, that the opponent, the minimizer, can force. It starts at positive infinity, because the opponent is assuming the absolute worst-case scenario. As the minimizer finds clever ways to shut down our good moves, this beta value goes down. So how do these values actually move through the game tree? A cool way to think about it is this Snow White principle. Basically, a new spot in the tree inherits the alpha and beta possibilities from its parent. But the moment it looks down at one of its own children and finds a better outcome, it gets greedy and updates its own value. This constant passing and updating of information is the key to the whole thing. All right, let's just walk through a quick example to see the magic happen in real time. Imagine the AI is searching the tree. It gets to a point where it's the opponent's turn, the minimizer, and it finds one possible future that has a score of 3. So the minimizer sees that score of 3. Now remember, its goal is to keep the score as low as possible. So a 3 is way better than its starting point of infinity. It immediately updates its beta value to 3. This is its new guarantee to itself. It's thinking, okay, no matter what happens, I have found a path where I can force the outcome to be 3, or maybe even better for me. Now the search backs up a bit and starts exploring a completely different branch of the tree. This time, it's our turn, the maximizer. And we find a fantastic move that leads to an outcome with a score of 5. Awesome! So we update our alpha value to 5. This is our new guarantee. I have found a way to get a score of at least 5. And this This right here brings us to the magic moment, the one single rule that makes this entire algorithm tick. The condition for pruning a branch is simply this. When alpha becomes greater than or equal to beta, you prune.
And this is where it all clicks into place. Our maximizer is thinking, okay, I can guarantee myself a score of 5 if I go down this path. But it also knows that the minimizer has already found a different path where it can force the score down to a 3. A perfectly rational minimizer would never let us go down the path that gives us a 5 when it knows it has another option that gives us a 3. It's a logically impossible future, and so the AI doesn't waste a single brain cycle exploring it any further. Snip. The entire branch gets pruned.
That one simple, logical step has absolutely enormous consequences. It's what transforms this algorithm from just a theoretical curiosity into a practical, world-beating tool.
So what does all this mean in the real world? Well, without pruning, the number of possibilities grows exponentially. But with alpha-beta, in the best case, the growth is closer to the square root of that. And to put that in simple terms, for the exact same amount of computing power, the AI can see roughly twice as many moves into the future. That is literally the difference between a decent player and a grandmaster.
And this isn't just theory, okay? This is the engine at the very core of legendary game AIs. Chess engines like Stockfish use it to analyze millions of positions a second. And even though AlphaGo got famous for its fancy neural networks, its search component was a powerful mix of techniques that absolutely included the principles of alpha-beta.
But, as powerful as it is, alpha-beta isn't a silver bullet. It has some really important limitations that kind of point the way toward the future of game AI.
For one thing, its amazing efficiency depends on looking at the best moves first. If you happen to look at bad moves first, you don't get to prune very much. It also assumes your opponent is a perfect, flawless player, which, as we know, humans are not. We make mistakes, and for some games, the game tree is just so unbelievably massive that even with pruning, it's still too big to handle.
Which brings us to a final, really fascinating question. For decades, alpha-beta was the undisputed champion of game AI. But now, we're seeing new challengers step into the ring, like Monte Carlo tree search, and they're totally changing how AI explores the future. You could say alpha-beta taught machines how to think logically. But maybe, just maybe, the next breakthrough will teach them how to think intuitively. What do you think is going to be the next game-changing move?